Okay. Later, if you haven't scanned the QR code, I will show you maybe in the middle or at the end of the class. Okay, I think last time we are dealing with this instantaneous velocity, right? Okay. Okay. So to start off the wait. To start off with this class, let me draw a triangle here. Okay, from Pythagoras, I believe all of you should be familiar. We have this expression, right? It was introduced early, maybe when you are third grade. No, I'm not sure. Third grade or fourth grade, right? Around that time, elementary school. Okay, and then now imagine. Okay, imagine you are having circle. Okay, you are having a circle with some radius. Let's say r. Okay, you have the circle. Okay, and based on triangle, can you approach the area of circle without knowing at the beginning that the area of circle is pi r squared? So you know that this is pi r squared, the area, right? Okay. But pretend you don't know really this area. Okay, pretend don't know this. Okay, maybe it was in like really long time ago, in a really ancient time, and they are just discovered that there are certain ratio, okay, between the circumference of circle and the diameter. Anyone know what this is? This ratio is your so-called pi. Okay. Yeah. Okay. Now the question is still the same. Okay. Based on your triangle, so you know the triangle have the Pythagoras formula, and you know that the triangle has area half AB, right? Based on this triangle, so it's base multiplied by height. Okay. So based on this triangle, can you prove that the circle is getting this pi r squared? Can you make a proof? And it's related to limit. It's related to limit. Anyone has any idea how to approach the triangle and circle? So you have the triangle, you know the area of triangle, But pretend you don't know the area of circle. How you are going to approach that the area of circle is actually PR squared from the triangle. Do you have any idea how to do? You put the triangle where? You want to approach the circle in. So it can be having a triangle outside, okay, or inside. Outside or inside. To approach that, the triangle can go to circle. Which one? Inside. Inside. Okay. Okay. Let's say the triangle. Okay. The triangle. I'm making. For example, it has. Let's say this is the height. Okay. The height of triangle. Okay. And I have the other. This is the R. Okay. Okay. So we're still missing this red area here. Okay. How about we make not one triangle, but more triangles? Okay. Let's say we are making a polygon, which means we have like 3-side polygon. This is 3 sides polygon. We have 4, 5, 6. Okay, we try to increase. What do I mean by that is, let's try to make maybe okay. And each of the polygon, all of these polygon, we can separate like this. And you can have a lot of triangles, right? Okay. Let's say the number of triangles is n. Okay. The height of triangles is h. Or let me draw in the next page. Okay. Like this one. Okay. See here, the h is the height. Okay. AB is our base. Okay. So area of triangle is half AB h, right? If I'm making like 1, 2, 3, 4, 5, 6, 7, 8. It has 8. So the total triangle is half AB, H, and 8, right? So I get around this number, okay, for the total triangle inside the circle. Okay? This is if n is equal 8, okay? And we can increase our n, right? We can increase from like this is 6 and this is 12. And when you see the picture, okay, when you see this picture, when you increase n higher and higher and higher, it's getting closer to a circle, right? Okay, so approximating a circle as when we approximate the circle as the let's say the h, okay, the height is h. Let's see, as the as the n, okay, as the n larger, okay, we can see our h. See, h is here. This is h, right? Or if you see here, this is h here. Up until here. Here is our r. Okay? But here, this is h, this is r. When n getting larger, the h getting closer to what? To radius, right? H is getting closer to radius. So h getting closer to radius. It's getting similar to radius. So h getting closer to r. So this I have perimeter of the polygon. Perimeter means only the sides. Okay. So if you see this polygon, AB is the side. The number is 8. So 8 AB is my perimeter here. So perimeter of polygon is AB multiplied by the how many triangles are there. Okay. An area of polygon, I will write here. It's the same as the left one, but I will write here. It's half the perimeter of polygon, ABN and H, right? It's the same as the total of the triangle. So as H getting closer to R, so it will be half the ABN here is getting closer to our 2 pi r, circumference of the circle. Okay. So then I can rewrite this ABN with 2 pi r, and when h is getting closer to r, is getting r. So we can get this pi r squared. Okay. So as h, so we can write simply with limit as h getting r of our half 2 pi r h. We can simply substitute the h with r in our limit concept. Okay? Well, actually, when we approach with triangle, in reality, it will not have an exactly the same value, but it's really having a really small gap. But because we are dealing with our tools here, this limit, okay, we are using this limit, okay, because we are using limit, we can get the value, okay, because we're approaching some variables to some finite numbers. In this case, the finite numbers is our radius, our r. Okay? So from there, we can simply use our limit concept to approach geometry. Limit can be approached to geometry, any numerical or approximation, like in your calculator, your graph. You can use limit to approximate some number. Okay? And later, also in derivative, we can also approximate some number. I think the easiest one you can do in your calculator is using the linear regression. Right? It's the easiest modeling you can do in your calculator. Linear regression, if you are dealing with the curve, you can find a modeling called linearization, and you can have approximation to any case that you can model with linearization. But later I will discuss more in differentials, okay, derivatives. But this is just our intro for today, okay? The concept of limit. Okay, so actually you can use limit in any forms you want, approaching some geometry, functions. You can also do that. Okay, so the first section that I want to discuss is limit of a function. So here is the fx. This is the graph. Okay, this is the functions. So value of x near x equal 1. So I will write the function one more time here. So I have x minus 1 over x squared minus 1. Okay. If I plug in 1, okay, if I plug in 1, it will be our 0 over 0 situations. Okay? But when we see the graph, okay, when we see the graph here, let's say we have this is 1 here, and it says 0.5. Okay. I'm not sure in your calculator who has the graphing calculator. If you try, make the graph x minus 1 over x squared minus 1. Is your calculator showing just continuous graph or no? I'm trying using in GeoGebra. Why is that happening? If you zoom in the website or this GeoGebra calculator, actually, okay, they are using real scale. So 1 point is exactly 1 point. So when you are trying to zoom in, here's what happened. So it's actually discontinued here. So exactly at this point, there is something going on there. Okay, that is when we try to plug in 1, and in our functions we get the 0 over 0 situation, which is undefined. Okay, if you have 1 over 0, you can have infinity, right? Positive infinity. But when you have 0 over 0, you said it's undefined. Infinity and undefined is conceptually it's different. Okay, it's different. But let's see our graph here. Okay, if we are dealing this 1 x equal 1, we go from right, okay, to this point, and we go from left to this point. Okay, in our limit, okay, as x approach 1 from our function, it goes to some value 0.5. Okay, I will tell you how to evaluate limit, but later. But from this graph only, its limit is 0.5. Okay. You can also try, like I mentioned before, you can try make some point here. Okay, maybe 0.99999, or maybe 1.000001, and you keeping adding all the number, all the 9, all the 0, you will getting closer to 0.5. Okay, that's our proof from last week. Right? So at least from this graph, I will write, let me write here, okay? So definition, if you have limit as x approaching any number as your functions, okay? So meaning f or function defined when x is near the number a. Okay. That's what the limit is for. Okay. So it's defined when you are near that number a. And some open interval, okay, some open interval, they having a except not at a itself. Okay. What does it mean? This is precisely what we are dealing with, this graph. Okay. At the f1 from this graph, it's undefined, right? But its limit, okay, limit x1 is 0.5. Okay, so it can happen in limit. So you may have your limit, you have value, but when you plug in the x, it will be undefined. It can happen. It can happen. I think last night I sent some PDF. That is just for preparation for class. So I try to send every week what will we discuss. Hopefully we can discuss all the things that I've sent last night, or maybe for next Thursday. So here is the cases. Okay, okay, 3 cases here. First, this A. Okay. I think this is just a normal graph. Normal graph, all continue. Okay, there's nothing wrong. Okay, and you are using limit. I don't know why you're using limit here, but if you're using limit here, then that's just normal. Okay, this normal case. Okay. Normal function. So it's just you can find the limit and you can plug in the a into the function and it's continue. Okay, it's continue. The other case is when you try to plug in the a, you are confused. Oh, why? What's happened? It's undefined. That's why you see the hole here. Okay, hole. Or we say this is removable, or there's a lot of name, but I'm just choosing hole as it's easier. Or maybe point discontinuity. But it's just a name. I mean, as long as you understand, doesn't matter. So there's a hole, but you can find the limit. Okay, the limit as x approach a of our fx is some L here. We have the limit. Okay, and also another case is there's a hole here, but when you plug in, maybe we'll make this is m. Okay, when you plug in a into the functions, you may have another number different from L. Okay, and your limit as x approaching a from the functions is L. It's totally different. Okay, m and L. Okay, different number. It's also can be the case, okay? But the similar case in all of these three, okay? all three having limit. Okay, it's having limit as in L. That is the limit. Okay. Okay. And the graph on the bottom side, this is actually graph for fx is sine x over x. Okay, I want you to maybe thinking if proof limit as x approaching 0 of sine x over x is equal 1. If you see the graph here, this is the function. The function is sine x over x. When you approach 0 from left or right, it will approach 1. Okay, so graphically from the graph we can say that okay, it's 1. But how about if you didn't use any graph? How to prove that? Okay, we need another theorem called the Squeeze Theorem, but I will come back to this Squeeze Theorem later. Okay, later, maybe at near the end of the class. Okay. Okay, I want to go back to this graph. Okay. Okay, so you get the idea that when you have the limit here, it's getting to 0.5, right? We try to approach from the right side, we approach from the left side, right? And we get one conclusive answer, okay, which is 0.5. But what's happened when you approach from right side and when you approach from the left side, you have different approach. Let's see here, okay? When you approach the 2, let's say this is gx as x approaching 2. So what will you do here? So if you see it from left side and right side, it's different, then you can conclude that that is your limit. Let me write this in the new page. Okay. So we have tools. It's called one-sided limits. So limit as x approaching a negative of fx L. We call this left hand limit. This is x approaching from left. And then we have also, we call this a negative, a positive. Okay, you write the positive and negative like a index, like a power, like a square. So this is right-hand limit. So this is as x approaching from right. And then what's the conclusion from these two? The conclusion is limit. This will be true when limit okay. So this limit is true if the right-hand limit equal left-hand limit equals some finite number L. So that you can conclude that, okay, the whole limit as x approaching this, that number A is true, it is L. Okay, got it? Okay, so right hand, left hand. But from here, okay, you can actually see from the graph. But there's other alternative. You can see it only the functions and the interval, meaning you need to think of that interval. Okay. Usually it will define by, so this gx have, like for example, this gx has two functions, the first one and the second one, and it has different interval. Okay. This is maybe x2 and this second is 2. And maybe it is having also special case in x equal 5 here. Okay, but if you are dealing with this graph, okay, when we approach x equal 2, if we approach from the left, okay, from here, it goes 3, and we approach from right, it goes 1. Okay, it goes 1. So because it's not equal, so this is we can write, okay, because blah blah blah, then limit the of gx, you can write it doesn't exist, or dne, it doesn't exist. Okay. So I want to make sure that the mathematics in university is not always finding the from multiple choice. You have the questions, you need to find the answer. That's not all about this math. Okay. What's important in math is to learn the process, okay, to learn the logic process, why you are choosing that answer. Okay. So why limit x as x approach 2 it doesn't exist is because when you approach from left, it's different from what you approach from right, because it has different value, so limit doesn't exist. So it has like step-by-step logical reasoning. That is tools that actually you are needed in not only in your university career, your academic, after you get work, you go to work, that logical reasoning is helpful. Okay. It's not always about counting number, but when you are dealing with person, when you are dealing with maybe works, how to solve the work, how to finish the work, you need that step-by-step logical reasoning. Okay. And if we try the same thing, go for 5, okay? As we can see in the graph, it's having a limit around here, around 2, right? It's around 2, because when we are approaching from left and approaching from right, it's the same, it's 2. Whatever the case in x equal 5, like for example, when you plug in 5, it's actually maybe it's this is maybe 1 point something here, maybe 1.2 or 1.3. Still, the limit exists here, okay, for the 5, for x equal approaching 5. Okay, any questions so far? Okay. Wait for a moment. Okay, some online students want to see this page. Okay, so the conclusion is limit x approach a of the functions is L. That is true for left hand limit is equal right hand limit. Okay, I think that's clear enough. Okay. I notice some of you are using iPad, right? Which software do you use to write? GoodNotes, no? Notability? Oh, okay. Who are using GoodNotes? No? GoodNotes? No one using? Okay. If you are using GoodNotes, I can airdrop my file to you after the class if you want. But if not, I'm uploading the PDF. I think in Notability you can also using the PDF and you can write the PDF, right? Okay. So you can check the last night PDF I've sent to your email. Next week also I will send, and you can, if you're using an iPad, you can upload, download, and then put in your iPad, and you can write in your apps. I think that will help. Okay. That's for the one side limit. Okay, next page. I think I will go directly here. So if you see here, okay, this is 1 over x squared. Okay, 1 over x squared. You see in the 0, okay, it's getting higher and higher if you are using any software. You can try to go up and beyond, and I'm not suggesting that it will be ramp up your PC or laptop, and maybe it will have exhaustion. Okay, so just thinking of this graph, it's getting large. Okay, larger here, getting larger and larger. So we can say it's getting close to some infinity, positive infinity here. So if we are dealing with the limit as x approaching 0 from this equation, we can say that the limit is getting larger and larger. You can say it is. You can write this as as 0, or I will write this as the value. Okay, as the value of f of x can be made arbitrarily, or you can just write it can be made larger. Okay, as we please by taking sufficiently to some number, or you can say this is closer. Okay, yeah, I think it's easier. Closer to some number a. Okay, like this is 0. Okay, so limit x approaching a of fx is infinity if, okay, if we try to put some value there, and then the value in nearby the a is getting larger, so we can say it's infinite. I want to make distinction between the undefined and infinite. Okay? So if fx is 1 over x squared, okay, so if fx is 1 over x squared, it's, you want to say infinite, but actually in our case here, we say it's undefined. Yeah, in some case you can say it's infinite, in some case you can say it's undefined. But what does this limit means? Okay, you have any large number that you can imagine, because it's so large that you cannot make some exact number. You say it's infinite. Okay? This is called the infinite limits. Because infinite itself is, you can say, is large, but you cannot use that infinite in calculations, right? That's why when you have the interval, okay, you have the open interval in limits. Like for example, when you write the infinite, like all real number is, you have this open interval, because the infinite itself, it's abstract. It's not a number, okay? Not a finite number. Okay? Okay. Similarly, this is positive infinity. Similarly, you can have functions, and then it may have a negative. So it is negatively larger. The idea is the same as the positive one, but it's negatively larger. So it's larger, but in negative. Also, these two infinite limits, you can approach with the right hand, left hand, one side limit. Like for example, here, you can go from right, you can go from left to the x equals 0. Yeah, if you see in the big picture, it will be getting closer to infinite number. It's getting closer to infinity, like really large. Okay? So going from left, going from right. So it's going from 0 negative, it's going from 0 positive. Okay, so it seems we have in the middle here, in the 0 part, some line, okay, in which this line, the graph will not touch the line, right? Will not touch this red line. Okay? So in infinite limits, we may have the vertical asymptote. Okay, vertical asymptote. I will draw in another page. Okay? So let me draw in a new page here. can have this. You can have this. Oh, wait. So you can have the, let's say this is x equal a. At this x equal a, okay, the vertical line this is vertical asymptote of f of x or of y equal f of x. So limit, if you have limit x approaching from the right of ln x, it will be, if I draw this line, and this is 1 here because log 1 is 0. So I will have like that. So when you approach from right, and it will never crossing the y-axis for ln. So you can say this is negative infinity. Okay, one more thing here. If you have this graph, okay, the fx is this. Okay, fx is 2x, and you have the vertical line. The asymptote is x equal 3 here. So by using the one-sided limit, we can say that limit from the right side, it's getting infinity, right? Positive infinity. And from the left side, it's getting negative. But because this is not the same, then this doesn't exist. Okay. So if you given functions like these functions here, okay, if you can draw the graph easily, you can draw and see the picture. But if not, then try some interval, putting some interval, and see what's happened in the fx, okay? Whether it is going up or going down. Okay, and then you can make a conclusion whether the limit exists or not. Okay, another thing about limit, we have limit law, okay, which means we have certain algebraic operations in limit. Okay? So I will write this limit law. Notes, suppose the c is constant, any number, and limit as x approaching a of fx, and limit x approaching a of let's say gx. Both are of this axis. Okay. Okay. So one, you can add or subtract. Okay, we are still in this same similar meaning, and you can separate this into separate limit. If you are dealing with any constant c, you can factorize the constant going up outside. And if you multiply the functions, you can also separate. Okay, sometimes you need to rework the law to solve any problem. And also you have limit as x approaching a, f of x over gx. This with notes if limit is not equal 0. If not equal 0, then you can find and you can use this limit. Okay, I think most of you are familiar with all this law, because without you are realizing what you're doing, you already know how to solve some limits. Okay, because I think this law is quite intuitive in math, so doesn't really need to be memorized. Okay, let's try to take a look at this f and g as in this graph. Okay. The f is the red line, g is in the black color. Okay. The question is approaching -2 here. Yeah, -2. I think this is not too difficult. Okay. Finding the limit of f of x. So for g you get -1. For f you get 1, right? And then plug into the solution, you get the answer. If you have this f and g, 2 is here. I think 2 is the number is not good. Let's try to change to 1. Yeah, 1. I think it's better. 1 is here. For f, it's 2. For g, is around -1. And you can just simply use it. But I think because the g has 2, if you approach from here and from here, this g doesn't exist, right? So the whole thing will be doesn't exist. And if you have x approaching 2, fx over gx. Okay. If you have any fraction, like a rational functions like this, try to solve the g first. Okay, try to find g. G in this 2 here. So limit x to gx is actually 0, right? So the whole thing here doesn't exist also. The whole thing here. Because limit of the gx is 0 here. This part doesn't exist also, the g here. If you approach 1, it has this part and like this part and this part, right? You have to, if you approach 1 from here, so from this limit x approach 1, the g will be doesn't exist, right? Because this doesn't exist, all the f and g doesn't exist. And for this one, because this is 0, the limit is 0, so it will be doesn't exist. Because to have this f over g works, the g should not be 0. If not, it will be doesn't exist. Okay. Okay. Some notes. Power law. So limit x approach a. You can power the n like that. And you have also root. You can all the way below the root, you can move the limit. Okay, both of this, you need to have n is. Do you know what this means? The symbol. The symbol, do you know? It's called the integer. You know integer? Okay. So you have natural number, integer, quotient, okay, right? Real number, and complex. Okay. It's kind of similar to z because we if we want to read the integer, it's called Zahlen. Zahlen is from the Germany words for counting. So integer we call this Zahlen. So the integer for the n should be in positive. Okay, all of this should be in positive integer. Okay. Another notes, I think you need to know this. If this is only a constant, then it's a constant. Okay. Also, if it is a x, you can direct substitute. Okay. So it's called direct substitution. So if there's nothing wrong, you just change the x into the number, and if it is still logical, makes sense, then you can do it. Okay? Unless it's getting 0 over 0 situations. And also the power law, you can exchange that. The root law also the same. So if this is x, then you can direct substitute. So if you have x, getting to a of fx, you can direct substitute and getting a there. So this is the first thing to do to evaluate limit. Just plug in the x into the functions. Okay. Okay. So it's called the direct substitutions. Okay, I will just make a review for limit. Okay. Or any questions? Any question first? Okay, if not, then I will give you resume if you are dealing with limit. Okay, and I think it will be used for all limit problems. Okay, so how to evaluate limit? First, plug in to evaluate. 3, is it indeterminate form, or it's 0 over 0? Okay, so if you are having fx and limit is approaching to a number a, okay, so you try to substitute fa. Okay. You may have 3 possibilities. First, your fa will be maybe some number but over 0. This case, you may have the vertical asymptote. The second case, you just find the number, then done. Everyone happy. Okay. And the third case is 0 over 0. So when you find a 0 over 0, there are several ways to solve. At least 4, 5. I will write 4 first. So first is factorize. Second is conjugate or rationalize. Maybe you don't know the term, but actually you already know from high school. The last or third is trigonometry identity. The fourth is approximation. I think we will not discuss this approximation. And the other part is called the L'Hopital rule. We will discuss L'Hopital rule after we go in a few sections. But for now, we are dealing with the factorize, conjugate, and trigonometry identity. So approximation here, you can say the approximation are using a table like I did before. Like you put, maybe you're approaching 0. Maybe you are trying 0.00001. You make a table, you make conclusion, something like that, or any approximation method. But we will not discuss that approximation. We will try to going to first factoring, rationalize, and trigonometric identity. I think we can go for some examples. Okay, let's try x squared plus x negative 6. x minus 2. Okay, and one point that I want to tackle here, we are not only finding what is the real number for the answer, but what is actually going on with these equations. Okay, so you see, this is our function here. Okay, our function is this whole number, okay? This whole equations, x squared plus x minus 6 over x minus 2. So when you are factoring this, okay, when you're factoring, for example, making it x plus 3, x minus 2 over x minus 2, right? You're canceling this, right? And you have, oh, x plus 3. I want to ask you, does x plus 3 the same or not with f, with our original function? No, right? No. So what actually happened is you're having fx, you're having two conditions. Okay? First is when you plug in the, or I will write this x equal to. So when you plug in 2 to our functions, and it is 0 over 0, right? So this will be x squared plus x minus 6 x is not equal to. Or you can say, let's say, it's easier to say this undefined when x equal 2. And it will be x plus 3, but x is not equal to. At least there are some conditions. Okay, so this is different functions. So usually the questions in this kind of limit, okay, try to find or try to assign some value that making this limit exists, or that making this limit has a finite number, finite solutions. So if the question is asking exactly finite solution, what does it mean is we need to find the number that when we try to solve through factoring, it's making sense. Okay, it's not undefined. So the question is actually precise. Okay, but I just want to remind you that this is not the same functions, but maybe this is g here. Yeah, any functions you want to name. Okay. So when we try to factoring, and then when we try to plug in the x plus 3, it's 5. So when it is x plus 3, it's not equal to, we can get 5. This is factoring. Let me write this is factoring. And the, let's say I have another fx. I will this line here. Another fx, x plus 1 the question is limit as x approaching -1. Yeah. If you plug in, okay, before factoring and do other method, you need to make sure that it will work if it is 0 over 0. If not 0 over 0, then just answer as it is. If it's 0, then 0. If it is like having vertical asymptote, or saying it's having infinite amount. But if 0 over 0, then you can tweak the functions. You can change the form. Okay. But remember, when you change the form, it's not the same function as before. It's not the same as the original function. Okay? So when you plug in the -1, of course, this will be 0 of 0 here. Okay? So the second method we call the rationalizing. Pretty much, I think you already know. So if you have 1 over square root of third, when you want to rationalize, you can rationalize like this. Okay. And when you have this some square root and then a negative sign, then you need to put the positive sign. So rationalize so this negative, you need to multiply with the positive sign here. Why I need to make it positive? Because okay, from here. So you want to make an easier or simpler form. Okay? So let's try this. X plus 1, x plus 5, long line here. And then x plus 5 square root, it's x plus 5. -2 plus 2 is canceling. And -4, so x plus 1, right? Remove that, and we get this expression. So when we are asking to determine the finite numbers of this limit, then the limit will be limit of x -1. It's actually 4. But again, when we are removing this x plus 1, canceling each other, it became the other functions. It's not the same function as the original one. So what's happening is the same as before. It will be undefined on some point, but it will be defined at other points. I think you already done this in high school, right? Or did you forget? No? Okay. The next one is trigonometry. Trigonometry, if you have a limit of the function is 1 minus cos theta to sine squared theta. Yeah. I think it's quite doable. And you need to make sure first, when you plug in, it's 0 over 0 situations. Then you may use this as your function. And you want to use the trigonometric identity. Okay, of course, this is, you remember this, right? And then exchange the equation here to 1 minus sine. Again, when I'm trying to make some change in the form, it's not the same function here. Maybe I will change this to g or any function. But make sure you are writing that in different note, not using the limit, okay, to make sure that it is different. And then writing all here is becoming, wait, it's cos, sorry. It's cos squared. So it's 1 minus cos theta and 1 plus cos theta. And then again, we can simplify this. and we can have 2 plus 2 cos theta. Then we can input the limit at the very end. So it's 1, 2 plus 2 is 1 over 4. Okay. Then what is really happening is you have the f theta, you have the some parts undefined, some part is defined, which is the x should be not equal 0. This is when x is 0. My suggestion is try to remember the trigonometric identity, especially the like sine 2 theta. Remember 2 what? What is sine 2 theta? 2 sine cos sine, right? Okay. And then cos 2 theta. Remember the just the basic one. Okay. I think for calculus 1, this 3 will be frequently occurs, and it can help you to solve the trigonometric. Okay. Okay. Okay, next part is the squeeze theorem. Okay, the squeeze theorem. I think it will be the last session today. The squeeze theorem. So I will explain the squeeze theorem first, and then we can try to apply to our question before that I'm asking. The sine x over x. Let me write sine x over x here. We need to prove that. Okay, let's try to go into our discussion on squeeze theorem. So if I have a function, let's say this function, and then that function, and then that red one, okay? Let's say the blue is h of x, the green is the gx, the red is f of x. From this graph, okay, at the certain point here at the middle, we can see that f is less or equal than g, and g is less or equal than h. Okay. Let's say this is some point C, and it is approaching some number L here. If, okay, limit as x approaching C of f of x, this is L, and limit as x approaching C of the h of x is also L, then limit as x approaching C of gx is also L. So this is our right here. Okay. So if the functions f is less or equal g and g is less or equal h, you know the functions, the first, okay, the very below, you know it's going to have some L. and the top one is also the same, L, then your middle functions that stand between the f and h, it will have the same L. Okay. Okay. So this theorem, you can use it if you have f less or equal g less equal of h situations. So if you have these situations, you can implement the squeeze theorem and find the limit. Okay, and this theorem, I want to try to find our approach, okay, to prove limit as x going 0 for sine x over x equal 1. But I need to draw the geometry first so you can see how I will deal with these situations. I have two approach. Okay, I have two approach. Okay, first is based by line, the line in the geometry, and the second is the area. I will maybe I don't have time for two, maybe only one, and then later in Thursday I will continue the second approach. Okay. So I will write first. Okay. So your circle, imagine that your circle or let's try to make some triangle here and then make another triangle here. Okay. So I will name the O, and also I will draw the straight line here. Okay. O, A, B. Okay. And then I have here is the C. And maybe this is E, and this is D. So O, okay. So OB is the radius, and also OA is radius. Let's say our radius is just 1. We fix the radius at 1. And then we assume, okay, we assume the theta here, assume theta from 0 until pi over 2. So it will stay in all positive. Okay. The first quadrant, okay, 0 to pi over 2. Okay. So you see AB, okay, AB, the curve AB, the arc, okay. AB here, AB. We say this is arc AB. Okay. Anyone remember how to find the length arc? Remember? Anyone remember? You need to use the theta, but you need to multiply with what? Remember? No? Okay. So arc AB is R and multiply by theta. Okay. That's the length. Okay. Remember? Okay. Okay. So arc AB, because R is 1, then we can say arc AB is theta, just theta. Okay. That's first one. And then see the OBC triangle. Okay. Consider OBC, the triangle. Okay. Or should be here, triangle OBC. Okay. If I have the sine theta there, it will be BC over OB, right? This absolute value is just making sure that all are positive. Okay, sine theta is this. So I can rewrite in BC, because our OB is 1, radius, okay, is our radius. So it will be sine theta. Okay? So our goal is actually, let me give you some notes here. So we need to compare BC, compare AB, the straight line AB, and the arc AB. If you see from the geometric perspective, okay, this will be, or you can say it's less. But it's all connected to B, right? Here. BC here, AB is also connected here, and arc AB is here. That's why we can use the squeeze theorem. Okay. So from here, okay, because this is, oh wait, I forgot the absolute value. So from BC and arc AB, we can say that this is already happened. Okay, we have theta from the arc AB and BC from sine theta. We need to know what is AB. Okay. Let's see our AB from AB. Okay, if we see the triangle, okay, let's see the triangle there. AB is less than AE plus AEB, right? Okay, so this is AB here. The length, of course, you need to have longer here. AEB is longer from geometric perspective. Okay. Or let's say this is arc AB. It's also still longer, AE plus EB. And if you see AE and ED, okay, of course the arc AB is less than this, right? AE plus ED. Okay. This is, I'm guiding you one by one to see the geometric perspective. That of course is less. Okay. And from the picture, the triangle, we have two triangles, at least the small one and the bigger one, okay? At least two, if you not consider the other one here. So we have OBC as our sign here, and we have OAD. So consider OAD. So OAD, if I'm taking tangent theta here, if I'm taking tangent theta, then it will be AD over OA, right? OA is just our radius, 1. So our AD is our tangent theta. So this is our AD, right? So our arc AB is less than tangent theta. Okay. So our theta is actually less than tangent theta. Okay. I can rewrite the tangent in sine theta over cos. And then I can flip the theta and cos. So cos theta less than sine theta over theta. And from before, sine theta is less than 1. Okay. and then input all the limit value. And because this is 1, and it's also 1 from constant. So from Squeeze theorem, based on Squeeze theorem, this is also true 1 by Squeeze theorem. That's one way. I have a second way, but I think we don't have time for the second one. The second way is using the area of triangle. So you need to make a function of the area of triangle, and then basically you need to have 3 functions. Okay, the triangle, small triangle, the sector, and then this big triangle. You can use also that 3 functions. For this one, you are actually comparing this BC, AB, and arc AB. Okay, at least you get some idea. But Squeeze theorem itself, you can do in many occasions, in many functions, as long as f less g less h. You can have, if you have that situation, you can use the Squeeze theorem. You just need to prove that the first one and the third one is the same L. Then you can prove that, oh, the middle one is the same. That's the Squeeze theorem. Okay. Okay, I think I will stop here. Okay, I will stop here, and we can continue next Thursday. Okay. So if you have any question, you can come to ask me. Okay, for the online students, do you have any questions? Do you still need to write? If you need to, yeah, I can wait for 2 or 3 minutes. Okay, online students, if you have questions, you can ask. Is it clear? The Squeeze theorem?
How the should be integer? Could it be the something like 1.5 or 1 point?
Later, I will explain one more time. Okay. Okay.
Can you show me the last page?
Which one here? The before here?
Yes, yes.
Yeah, here. Yeah.
Thank you.
Okay. Okay, the material for the Squeeze theorem I will put in the PDF for the Moodle. Okay. So every week I will put some material for 1 week at least. Okay. Yeah, wait.
I have a question. I don't know why when we find the limitation, yellow over yellow, so we have to do another process. Why?
Because 0 of 0, we cannot know what form it is. That's why it's called the indeterminate form. So we need to, if we want to know some definite answer or some definite number from, let's say, from the limit, because we want to approach something, but that something is actually like it's, you cannot solve it right away. So you need to pick some some idea. So when you are 0/0, usually you have some undefined and some defined. And when the question is asking some defined, then you need to rewrite, and you can use the factoring, rationalizing.
So can you give me in the graph because like the case of a 0 to 0 because I think it's better if we have
Yeah,
the graph.
0/0, you can graph, and you can see in some point. I will later show you later in GeoGebra, maybe next Thursday. The graph, you will see the graph is like a continue, but when you like zoom in to some point, you will see it will be some hole or some discontinuity. Yeah.
Profit with
Mhm.
this area,
Mm.
but I don't know if is it correct. I use the two triangle area and one section.
Yeah, the small triangle and the sector, and then this the big
Sector,
yeah. Yeah, I think it's correct. I think yeah, I think it's correct.
It's stem, right?
Yeah, yeah. Good. Okay, you can scan the QR code if you haven't. I will give you 1 minute, and then I need to finish this class. Yeah, the class is finished actually.